All right, let's jump right into this explainer. Today, we're going to build a real, physical intuition for how charges create these completely invisible landscapes of potential energy all around us. We're going to take the, let's be honest, somewhat complex formulas of electrostatic potential and capacitance right from our source material and break them down so you can truly visualize the physical forces at play here. Yes, we are dealing with invisible dynamics, but by the end of this, you'll see them as clearly as hills, valleys, and structural foundations.
But first, before we get totally bogged down in the math, think about this for a second. What actually happens when you force a positive and a negative charge together? Does that create chaos or stability? Keep your answer in the back of your mind, because that simple physical interaction literally unlocks the core of everything we're about to cover. The entire invisible landscape is governed by that exact tension and release.
Okay, here's our roadmap for exploring this landscape. We'll be moving chronologically through these 6 core concepts: work and energy, defining potential, gradients, dipoles, equipotential surfaces, and finally, what actually goes on inside a conductor.
Starting with Section 1, work, energy, and charges. Basically, the struggle against the electrostatic force.
Picture this. You've got a massive source charge acting as a Don, sitting incredibly comfortably in its territory. Now, say you want to bring a small test charge, a little thug, from infinity all the way into the Dawn space. Well, if they share the same positive charge, that thug isn't going to go willingly. At all. The source charge relentlessly repels it. You have to apply significant, deliberate external force to physically drag it in against its will. Every single inch you push forward requires energy, basically turning empty space into a hostile battleground.
Now catch this detail, you have to move the charge slowly. Why slow? Because by moving it with constant velocity, the kinetic energy stays firmly at 0. And the work-energy theorem tells us that if there's no change in kinetic energy, all of that intense external work you just exerted dragging the charge, it's captured and stored directly as a change in potential energy. You are, quite literally, winding up a microscopic spring.
Moving right along to Section 2, defining potential and energy. It's time to separate the joules from the volts.
People mix these two up all the time, and it's surprisingly easy to do. Potential energy, measured in joules, is the total work done to assemble the entire system of charges. But potential, which is measured in volts, is the work done per unit charge. So potential is simply the potential energy divided by the test charge itself. You're effectively kicking the thug out of the equation entirely just to purely measure the environmental effect of the source charge's territory. You're isolating the landscape itself from the object moving through it.
And that leaves us with this gorgeous, simple little formula. V equals K times Q over R. This represents the electric potential created by our source charge, capital Q, at any given distance R. It proves that as you step further away, the potential doesn't just drop off in a straight line. It falls off in a distinct curve, which physically shapes that invisible landscape we're talking about. It's a slope that just gets gentler and gentler the further out you go. Okay, but what if you're tackling a complex system, like, say, a triangle of multiple charges all interacting at once? You can actually find the total potential energy of the whole setup just by following a simple 3-part sequence. First, isolate and form pairs of all the individual charges. Next, calculate the energy for every single pair you've identified. And definitely take special care to keep their positive or negative signs here, since energy is a scalar quantity. Finally, just sum those values algebraically. That final number? That's the total energy holding the entire group together in that exact configuration. All right, Section 3, potential gradient and fields. Let's map out those invisible hills and valleys.
Take a look at the potential gradient equation because it tells a really fascinating story. E equals negative dV over dr. See that negative sign? It's incredibly critical. It essentially proves that as you walk along the exact direction of the electric field, your potential value is continuously dropping. The field actively points down the steepest possible hill of potential. So the math is directly translating into the physical slope of our landscape.
So how do charges actually act here? Well, positive charges act exactly like boulders. They naturally want to roll down the hill, moving from high to low potential. But a negative charge does the exact opposite. It naturally climbs up from low to high potential. And this completely answers our opening question. When you allow opposite charges to come together, you increase stability and lower the overall energy. But forcing like charges together, oh man, that builds immense tension, massive instability, and skyrocketing potential energy.
Which brings us to part 4, dipoles, or pairs of charges, the dynamic dance of equal and opposite charges.
This is wild. If you measured the potential anywhere along the equatorial line,
which is the axis slicing right down the absolute middle of a dipole. You get exactly 0. Anywhere along that precise bisecting plane, the opposing potentials perfectly cancel each other out. The net potential is always just a flat 0, showing this perfect symmetry in the space around it.
And this dynamic perfectly explains why a dipole facing backward in an electric field acts like a literal ticking time bomb. When it aligns perfectly with the field at 0 degrees, it rests in stable equilibrium, totally chilled out at a minimized negative energy state. But flip it 180 degrees so it directly opposes the field, now it's in unstable equilibrium at a maximum positive energy state. It's just sitting there, highly unstable, waiting for the absolute slightest nudge to violently snap back to a position of stability. On to Section 5, Equipotential Surfaces, or EPS for short, the flat plateaus of the electrostatic landscape.
Think of a topographic map. Just as that map has contour lines of equal elevation, our electric landscape features equipotential surfaces. The geometry of the source charge directly dictates the physical shape of these plateaus. A point charge radiates outward into expanding concentric spheres. A straight wire stretches out into coaxial cylinders. And a massive uniform plane sheet? It projects straight outward into perfectly flat parallel planes.
Here's the really cool part. Because there is absolutely no difference in height or potential across an EPS, walking a charge anywhere along its surface requires 0 external work, none at all. Visually speaking, the electric field lines will always slice through these surfaces at a strict 90-degree angle. Plus, if you step into a region with a much stronger electric field, you'll see these equipotential surfaces bunching way closer together, exactly like steep contour lines on a mountain map telling you you're near a sharp cliff.
Now here's a massive trick for your exams, and it is highly counterintuitive. Attracting charges actually produce repelling equipotential lines. Seriously, if you put a positive and a negative charge together, their EPS lines will actively bend away from each other. But if you put two repelling positive charges together, their surfaces will warp inward, attempting to attract and overlap.
Finally, Section 6, Inside a Conductor, the hollow shell of electric fields.
Whether a conductor is solid metal or completely hollow inside doesn't matter. The electric field anywhere within that material drops straight to 0. Why? Because any excess charge introduced to a conductor violently repels its neighboring charges. Everything instantly scrambles to the extreme outer surface to get as far away from each other as physically possible, which leaves the interior totally empty of field lines.
Okay, myth bust time. Many people assume that a 0 electric field automatically means 0 electric potential. But nope, that's a huge misconception. Remember our gradient equation? If E is 0, it just means the potential isn't changing. Because the field is 0, the potential remains entirely static from the outer surface all the way to the absolute center. The entire inside acts as one massive, constant equipotential volume.
So as we wrap up this explainer, I want to leave you with a bit of a brain teaser right from our sources to test your newfound physical intuition of this invisible landscape. If the potential inside a hollow conductor is completely constant, perfectly locked at whatever the surface value is there any specific point in that system, besides infinity, where the potential could truly drop to 0? Think about the forces, the gradients, and those dancing charges we've covered today. Keep exploring that thought, and I'll catch you on the next explainer.